Okay, so everyone, welcome back. So in this video we want to talk about the axiomatic approach to probability, and basically what that is that, but in earlier sections of this chapter, we have considered random experiments. We have talked about random experiments. We have talked about the sample space of those experiments, and we have talked about the different events associated with those experiments. So we talked about the events associated with those experiments. Now, in our day-to-day life, we use many words about the chances of occurrence of events. Probability theory attempts to basically quantify these chances of occurrence or non-occurrence of those events. And also in the reviews that we did related to probability, we have studied some methods of assigning probability to an event associated with an experiment, having known the number of total outcomes, and then basically then using that sort of information, we calculated the probability of a specific event happening. Now, the axiomatic approach to probability seems to be a little bit different, meaning that using this method, what we do is, well, I read this once, and to be frank, I didn't really understand it that well, so let's read this together and see if we can make sense of it. So basically, axiomatic approach is another way of describing probability of an event. It's basically another way of doing the same thing. But in this approach, some axioms and rules are depicted to assign probabilities. Now let's go through those rules and see what they are. So let S be the sample space of a random experiment. So let S be the sample space of a random experiment. The sample space of a random experiment. Now, the probability P is a real valued function. The probability P is a real valued function whose domain is the power set of S, whose domain is the power set of S, and the range is the interval, and the range is the interval 0, 1. Actually, the closed interval 0, 1. Satisfying the following axioms. satisfying the following axioms. So the axioms are: for any event E, P of E is greater than or equal to 0. Number one, for any event E, P of E is greater than or equal to 0. And P of S is equal to 1. Number two, P of S is equal to 1, meaning that S being the sample space, P of S is equal to 1. And number three, if E and F are mutually exclusive events, if E and F are mutually exclusive events, then P of E union F, is equal to P of E plus P of F. If E and F are mutually exclusive events, mutually exclusive meaning that they have, the two events are basically, if you look at them as sets, they have nothing in common, meaning that the basically E intersection F is equal to the null set. If that's the case, then P of E union F is going to be equal to P of E plus P of F. So that is basically now the sentence that we have here needs to be understood. It says that let S be the sample space of a random experiment. So this is clear. You can understand that, of course. Let S be the sample space of a random experiment. You know what a random experiment is, and you know what the sample space is, so we have no problem there. Now it says that the probability P is a real valued function. So you need to understand what the real valued function is, where basically domain is the power set of S, and the range is the interval, is the closed interval 0, 1, satisfying the following axioms. So for any event E, P of E is greater than or equal to 0. Of course that makes sense, because it shouldn't be, I mean, definition wise it doesn't make to say that the probability of some number is less than 0. That doesn't make any sense unless you define it in some way and give it some meaning. But as far as I understand and as far as I know, there is no, I haven't seen much about probability, of course, but I have been doing even some university courses in mathematics, and I've never actually seen a negative value for the probability of some event happening. It seems that they have not defined it in mathematics. Not that it couldn't be basically correct mathematically. Of course, if you define it, you can use it in mathematics. There is no problem with that. But I think that they have actually not done that. Okay, so basically the first axiom is that for any event E, P of E is greater than or equal to 0. Meaning that if it's an impossible event, then the probability is 0. Otherwise, it's greater than 0. Now, P of S is equal to 1 because S basically, it does contain all the different outcomes of the experiment. So then basically P of S, of course, is equal to 1 because that's the probability of all the different single or simple events of that experiment. And of course, as you can see, if E and F are mutually exclusive events, as you can see here, if E and F are mutually exclusive events, meaning that suppose that, for example, E and F are basically suppose that E and F are basically, suppose that, for example, your S has basically, you have this sample space, meaning that you have S1, you have S2, you have S3, you have S4, and you have S5, for example. So you have basically these five members of the sample space. So of course you know that S1 and S2 are mutually exclusive events. These are mutually exclusive events because they are single events, or not single events, but the terminology, the right terminology to use here, they are simple events. They are simple events that basically belong to S. They are simple events that belong to S. So since they are simple events of this experiment, of course they are mutually exclusive, and we have already talked about this, and it does make also intuitive sense. Now, if basically E and F are mutually exclusive events, of course suppose that, for example, you get some sort of probability for E and some sort of probability for F, but E union with F is going to be, for example, some set. Having this in mind, it would be something like S1, for example, S2, right? So now, of course, S1, S2, the probability of this would be P of E plus P of F. Now, I don't have enough reason here yet, but we will hopefully take a look at this in basically in an example or something like that to understand it. So let's see what. So let's now move forward. Now, from all of this discussion here, so we said that there are a few things that we need to first understand here. So first of all, okay, so now basically it says that the probability P is a real valued function. So for the sake of simplicity, you can just imagine that when they say a real valued function, what that means is just the notation, the notion of function that you understand. F of x is equal to, for example, some relationship, some mapping from basically some domain to some range, right? And now, but again, you can imagine that, for example, the range of this function, usually when you have a function, you have some domain and you have some range, and basically all of these elements in the domain are mapped to some elements in the range, right? This is basically usually what what you understand from the concept of a function. Now you can imagine that when they say a real valued function, you can imagine that the range of the function is the set of real numbers, meaning that if I call f of x, for example, if I call this f of x and if I call this x, then f of x belongs to the set of real numbers, something like that. If they say a real function, as opposed to the idea of, if they say a real function as opposed to the idea of a real valued function, so a real valued function is what I just said, is a function, is a mapping from some domain to some range, and this range is the set of real numbers. Now when it comes to a real function, you can also imagine that basically your domain also belongs to the set of real numbers, meaning that in the case of a real function, x and f of x both belong to the set of real numbers. That's basically what that is. So that's basically the concept of a real valued function and real function. Now, it says that the probability P is a real valued function whose domain is the power set of S. Now let's see what the power set is. I think the power set is so it says that over here on Wikipedia we had this in sets, but it says that in mathematics the power set or power set of any set S is the set of all subsets of S, right, including the empty set and the S itself, variously denoted as P of S, or I don't know what this notation is, using the Y stress P. I don't know what that is, but it's denoted as P of S or P of S, or identifying the power set of S with the set of all functions from S to a given set of two elements 2 raised to the power S. Okay, let me see what this thing is. Okay, so very simply, so for example, if S is the set, for example, x, y, z, then the subsets of basically the subsets of S would be basically first of all phi, or the empty set. Then you could have basically a singleton set, for example, an x or a y or a z. Or then you could take any of these two together, meaning that xy, xz, yz, and yx, and then you could have so you could have xz and xy, xz and xy, and then xz and xy, and then you have zy as well, right? And then you have also xyz as well. So that would be a subset of this set. And then you can you can basically, if now you put all of these sets in a single set, then you can call that set the power set of the set S. Let me write this down. So again, coming back to the same set that we had here, if you have some set S which is equal to, suppose you have X, Y, and Z, you have some set, for example, X, Y, and Z. So the subsets of S, are basically all of these sets. First of all, you could have the empty set. Then you could have, for example, the set containing only X. Then you could have the set containing only Y. Then you could have the set containing only Z. Then you could have the set containing, for example, X and Y. Then you could have the set containing X and Z. Then you could have the set containing Y and Z. And then you could have the set containing all of the elements, meaning the set itself. So you got basically 1, 2, 3, 4, 5, 6, 7, 8 elements here. And the number of subsets of a set depends, of course, on the number of, and of course we did this in the algebra of sets, but I have forgotten the whole thing really. But what I can remember is that the number of subsets of a set depends, of course, on the number of the elements that it has. And I think you could calculate it as 2 raised to the power of the number of the elements that you have. For example, call it 2 raised to the power p, where p is the number of the elements of the set, right? Now let's see over here if that works. For example, let's say that for example over here 2 raised to the power 3 is equal to 8, which is the number of subsets of this set. 1, 2, 3, 4, 5, 6, 7, 8. Now let's say that you have some other set, for example S1, and the elements over here are X and Y. So then the subsets would be the empty set. Then you would have basically X, then you would have Y, then you would have also X comma Y, and then you would have, that's it. So now if you write 2 raised to the power 2, which is the number of elements here, that gives you 4, which is the number of subsets here. So that's basically the whole story there. Now, and what happens is that now there is some concept called the power set. So the power set of a set, for example S1, is a set which contains all of those subsets of that set. Meaning that, for example, you can write the power set of S1 as this set, and the next set over here, and the next set over here, and the next set over here, and that's the power set of this set S1. And it's denoted by, and the power set is denoted by, as I can see over here, where am I? And the power set over here is denoted by P of the power set of, and the name of the set, for example in this case S1. This notation means the power set of the set set S1, right? So that's the meaning of the power set. We had this in the same books, basically. We had this in the algebra of in set theory, or basically the algebra related to sets. There was a chapter related to that in, I suppose, class 7, 8 or something like that. Well, I have basically I have actually forgotten most of the material there. If it's required, we will go back and take a look over there. So basically, what we had so far is the probability of the probability P is a real valued function whose domain is the power set of S. So the domain is the power set of S, meaning that in the mapping you have all of the subsets of S, and the range is the interval 0 to 1, meaning that what you're doing in this kind of probability, you're taking your S, basically your S is some set over here, and that set is basically the collection of all the possible outcomes of the experiment. That, by definition, that we call it the sample space. Now, since you have your sample space in this way, now if you write the power set of, if you rewrite the power set of S, you would get P of S, and of course you would get some set over here including some other sets, and so on and so forth. That would be the power set of S. Now basically we said that the probability probability P is a real valued function. We said that the probability P is a real valued function, real valued function with the following domain and range. So the domain of this function is the power set of S, S. The domain of this function is a power set of S, and the range of this function is basically the interval 0, 1, and the closed interval actually 0, 1. So because the value of probability cannot be less than 0, not greater than 1, it could be some value equal to 0 or equal to 1 and oscillating between the two values. So that's basically so far. And then basically this function does basically satisfy these axioms that we will talk about in just a few moments. Okay, so now the conditions that this function has to satisfy are that basically the first one is for any event E, P of E is greater than or equal to 0 for any event. It can be equal to 0, but it's not a negative number. Now P of S is equal to 1 because, as we mentioned before, S basically is the set that contains all the possible outcomes of the experiment, and if E and F are mutually exclusive events, then P of E union F is equal to P of E plus P of F. Now I don't exactly understand I understand what that means, but I don't know why they have said so. We will find out as we go along. Now, from 3, basically it follows from 3 that this one over here. It follows from 3 that so from 3 it follows that P of phi is equal to 0. P of phi is equal to 0. P of phi is equal to 0. Now to prove this, we take F is equal to phi. To prove this, we take F is equal to phi, the null set, and note that E and phi are disjoint events. And note that E and phi are disjoint events. Therefore, from axiom 3 we get from axiom 3 we get P of E union phi is equal to P of E plus P of phi, right? Or P of E is equal to, now of course over here E union phi is E itself, so you can say that P of E basically is equal to P of E plus P of phi plus P of phi, which means that P of phi is equal to 0, right? So now let S be this sample space containing outcomes omega 1 through omega n. Now let S be a sample space. Let S be a sample space containing outcomes omega 1, omega 2, omega 3, all the way up to omega of n, that is S is equal to the set omega 1, omega 2, omega 3 all the way up to omega of n. It follows from the axiomatic definition of probability that the axiomatic definition of probability that number 1, 0 is less than or equal to p of omega of I. Omega of I is less than or equal to 1 for each omega of I belonging to the set S. And number 2, p of omega 1 plus p of omega 2, p of omega 1 plus p of omega 2 is plus all the way up to p of omega of n is equal to 1. And number 3, for any event A, P of A is equal to sigma of P of omega I is equal to sigma of P of omega of I belonging to A. Now I don't understand this thing over here. So for any event A, suppose that this is some event, for example, you can think of that as, for example, some set over here having some basically outcomes here. Then P of A is basically equal to P of the sigma of P of omega of I belonging to A, meaning that the sum of the probabilities of each of these omega of i's that you find in A, basically, which is basically what we said before. So now it may be noted that the singleton omega of I is called elementary event, and for notational convenience we write P of omega of I for P of omega of I. So the singleton omega of I, basically you know that the singleton set is a set that contains only one element, and as a note we have it may be noted that the singleton basically omega of I, which is basically just a set with only one omega of I inside it, whatever that might be, but only one element there, is called an elementary event. Is called an elementary event, and for notational convenience we write P of omega of I, we write P of omega of I for P of omega of I. meaning that instead of writing P of omega of I this way, you write it this way, I suppose, and basically taking the fact into consideration that omega of I is a singleton. Now let's go a little bit further and see what we have here. It says that, for example, in a coin tossing experiment, we can assign the number 1/2 to each of the outcomes, heads and tails. So in the experiment of tossing a coin, the probability of each heads and tails, the probability of each of the outcomes heads or tails would be 1/2, right? That is P of heads is equal to 1/2 and P of tails is equal to 1/2. Number 1. And then clearly this assignment satisfies both the conditions, that is, each number is neither less than 0 nor greater than 1. The conditions that we had here were basically over here we said that for any event E, P of E is greater than or equal to 0. So this is one condition, and they must be talking about some other condition. Let me see. This condition over here. So we said that basically P of omega of I is greater than or equal to 0 and less than or equal to 1 for each omega of I belonging to S, right? So, and then P of omega 1 plus P of omega 2 all the way P of omega of N is equal to 1. And then we said that for any event A, P of A is equal to basically sigma P of omega of I for all omega of I basically belonging to the set A. And so I think they're talking about this condition here, which is basically, so this assignment satisfies both the conditions. This assignment satisfies both the conditions, that is, each number is neither less than 0 nor greater than 1. That is, each number is neither less than 0 nor greater than 1. And P of H plus P of tails is equal to 1/2 plus 1/2, which is equal to 1. Therefore, in this case, we can say that probability of h is equal to 1/2 and probability of t is equal to 1/2. Therefore, in this case, we can say that the probability of heads is 1/2 and the probability of tails is 1/2. Now, if we take P of h is equal to 1/4 in the same situation, if we take P of heads is equal to 1/4 and P of t is equal to 3/4, number 2, does this assignment satisfy the conditions of axiomatic approach? Now, does this assignment satisfy the conditions of axiomatic approach? Yes, in this case, probability of head is equal to 1/4 and probability of tail is equal to 3/4. We find that both the assignments 1 and 2, meaning that when we said in the assignment was basically, the assignment 1 was P of heads is equal to 1/2 and P of tails, we assigned basically 1/2 to that as well. So now we find that both the assignments 1 and 2, and this was basically 1, are valid for probability of heads and tails. In fact, we can assign the number p and 1 minus p to both the outcomes such that p is greater than or equal to 0, less than or equal to 1, and p of h plus p of t is equal to p minus 1 minus p is equal to 1. So, but of course, it has to be the right assignment. So it says that in fact, we can assign the numbers p and 1 minus p. We can assign the numbers p and 1 minus p to both the outcomes such that such that basically 0 is less than or equal to p is less than or equal to 1, and p of h plus p of t is equal to p plus basically 1 minus p, which is equal to 1. This assignment 2 satisfies both conditions of the axiomatic approach of probability. Hence, we can say that there are many ways, rather infinite, to assign probabilities to outcomes of an experiment. We now consider some examples. Now, of course, and let me write this down. Hence, we can say that there are many ways in many ways rather infinite to assign probabilities to outcomes of an experiment. To assign probabilities to outcomes of an experiment. Now let's consider some examples here and see what is actually, because so far I have understood the material logically, but I don't know where it's taking me. So let's do some examples, see how it's actually used really. Okay, so as an example, we have an example over here, example number 9, which is let the sample space be S equal to omega 1 through omega 6. So your sample space is equal to basically omega 1, omega 2, and all the way to omega 6. Which of the following assignments of probabilities to each outcome are valid? Which of the following assignment of probabilities to each outcome are valid? Which of the following assignments of, I need to write assignment properly, assignments of basically probabilities to each outcome are valid? So you have basically your outcomes here as omega 1, omega 2, omega 3, omega 4, omega 5, and omega 6. And A would be basically 1/6, 1/6, 1/6, 1/6, 1/6, and 1/6. B would be, for example, B would be 1, 0, 0, 0, 0, 0. C would be, for example, 1/8, 2/3, 1/3, 1/3, 2/3, 1/3, 1/3, and 0. And 0, and I'm sorry, there is no 0 there. So 1/3, 1/3, negative 1/4, and negative 1/3. And D is 1/12, 1/12, 1/6, 3 times, and 3/2 over here. And then you have E as basically 0.1 through 0.6, 0.1, 0.2, 0.3, 0.4, 0.5, and 0.6. So what that means is that I think that the condition that has to be satisfied is that the sum of all of these probabilities has to be equal to 1, and also is supposed to be equal to 1. And of course it's not supposed to be a negative number. It could be equal to 0. Let's see how they have solved the problem, because to be frank, I didn't quite understand the concept yet, so hopefully we will understand it through the examples. So the solution A, condition 1, solution A, so there seems to be two conditions here, and we're talking about solution A. Talking about solution A, there is the first condition, condition 1, which is each of the numbers p of omega of I is positive and less than 1. Each of the numbers p of omega of I is positive and less than 1, as you can see here. Number 2, sum of the probabilities is equal to 1. And condition 2, sum of the probabilities is equal to 1. Meaning that basically 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 is equal to 6 times, is equal to 6/6, which is equal to 1. So that means that the first condition is that each of the numbers p of omega of I, each of these numbers you can call them p of omega of I, for example p of omega of 1, p of omega of 2, 3, and so on and so forth. It has to be a positive number, and it has to be less than 1, of course. A positive number and less than 1. Meaning that we said that p of omega of I is basically supposed to be greater than or equal to 0, less than or equal to 1. That's condition 1. That's condition 1. And condition 2, p of basically sigma of p of omega of I is supposed to be equal to 1. Meaning that p of omega of 1 plus p of omega of 2, as basically I goes from 1 to n, for example, of course. P of omega of 1 plus p of omega of 2 plus all the way up to p of omega of n is supposed to be equal to 1. Because the reason here is simple, because you're considering all the different outcomes of the experiment, and the sum of the probabilities of all the different outcomes of an experiment is always, of course, equal to 1. Meaning that you're calculating p of s, right? The probability of the sample space, which is always equal to 1. And here, of course, for example, if you put all of these omegas together, basically all of these omega, the sum of, basically not the sum of them, but all of your omega of i's, if you put them together, you will get some set, which is basically your sample space. And of course, you know that the probability of your sample space is always equal to 1. and therefore the assignment is in this case valid. Now over here we said that each of the numbers, basically p of omega of y, is supposed to be a positive and less than 1. I think it can be less than or equal to 1. Now it seems that the condition that they have used for this case is pretty different. I will explain. So the reasoning that they have used here is basically for case B. They have, for the case B, they have written a condition. They have written a condition 1 as each of the numbers p of omega of I, each of the numbers p of omega of I is either 0 or 1. Is either 0 or 1. And condition 2, sum of the probabilities is equal to sum of the probabilities is equal to 1 plus 0 plus 0 plus 0 plus 0 plus 0, which is equal to 1. Therefore the assignment is valid. Therefore the assignment is valid. So now, of course, as we go through the chapter, as I mentioned before, sometimes there are some concepts that you have to basically wait and go through the problem so that they kind of start sinking in and falling into place. Otherwise, no matter how well you read something, sometimes you just don't understand it. That's sometimes just the way it is. Now for part C here, basically we have all of these probabilities for the different outcomes of the experiment, and it says that condition 1, 2 of the probabilities, p of omega 5 and p of omega 6, are negative numbers. Therefore the assignment is not valid, right? And so this is not valid. And part D is basically, you see all of these numbers are basically positive numbers, but this is 3/2, which is 1.5. And I think because of this, the assignment is not valid. Since p of omega 6 is equal to 3/2, which is greater than 1, the assignment is not valid. And over here, you see that all of these numbers are positive and greater than 0. Positive and, of course, well, greater than 0. And none of them is greater than 1. But the sum of them is 3, 6, but the sum of them is greater than 1. Therefore, the assignment is not valid. So that is also basically one thing over here. Now, let's do some more examples and see what we have here. Right, see you in the next video.